All right, here we had left off at part E, where we'd done a root locus of the original system with the compensator that was just proportional control. So here, proportional control, and we found we had some steady state error, and we had some overshoot, and you could take a look at the MATLAB code, and you could see the overshoot of the step response. So at this point, what we're going to do is we're going to take the original L of S, which we know to be 4 over s plus 1 squared plus 2 squared, and we're going to add a compensator that is of the form, we have s plus 3, a 0 at minus 3, and we have a 0 at 4, and then to get better tracking performance, we're going to put a pole at the origin to make this a type 1 system where it would track a step with 0 error. Okay, so this is our new L of S, and what I'd like to do is make the root locus for that and look at what could happen and how we could improve our control system. Okay, so let's drop in the original poles. Okay, so we had a pole at -1 plus J2 and -1 minus J2. Those are the two poles. And we're going to add a new pole, let's do a different color, a new pole here, and a couple of zeros at 3 and 4. Okay, so if we're labeling the points on the axis, this is -1, -3, -4. Okay. All right, so let's do the root locus. What we know is that there will be 3 branches. Okay, we know that n is 3, and there's 2 zeros, 2 finite zeros, so m is 2, and so that means phi is 180. Okay, so that helps us out. Then we can look at what happens along the real axis. Is the real axis part of the root locus? And so we know from our techniques that this will be a part of the root locus along the real axis here, and then we skip the middle part between the 2 zeros, and this will also be a part of the root locus. All right, so we then try to picture how would this work out to where it would generate this root locus, and so I can see this particular pole sliding over in this direction, heading towards that 0. Remember, all the poles head to a 0, either a finite 0 or an infinite 0. Okay, and then these two poles are going to travel some route around, hit in here, and head. One would head towards this 0, and the other would head asymptotically towards the 0 at infinity. So this is what we're thinking would be a rough estimate of what the root locus would look like. We could always go to MATLAB and get a more accurate picture. Okay? So I like this because before, as I increased gain, I was moving the roots to have a smaller and smaller theta, which would give us more and more overshoot. Okay, so I can control this a little better if I start increasing the gain and maybe arrive at a point over here and here for the root locus, and that would put another root somewhere along here, depending on the value of the gain. It looks like that has some hope of giving us a better response. Okay, and so that's what I would want you to argue on an exam, is that we have better overshoot response because theta is now a larger angle. All right, that was the main part of the question on overshoot. And then as you know, a side benefit, we also get this pole at the origin, which gives us improved tracking. All right, in part G, we're taking a look at a PID controller, and we know the form of a PID controller. All right, and so the question says, for the compensator from the previous part, so meaning this compensator here, express Kp, Kd, and Ki in terms of the overall gain parameter K that shows up in the controller. All right, so here's what I'm thinking on this problem. dc of s is of the form k, s plus 3, s plus 4 over s. And so we FOIL this out and we get the k, and we'll have an s squared plus a 7s plus 12, all divided by s. And we manipulate this into the form that we see here for the compensator, so we can identify the gain constants associated with the proportional, derivative, and integral parts of our controller. Okay, so when we do that, we would have k s squared over s plus 7k s over s plus 12k over s. And so canceling some terms here, this cancels, and I can see that my derivative term, kd, is just k. I can see my proportional term, kp, is 7k. And then finally, my integral term is 12k. All right, so that's the solution to part G.